Okay, so what I'd like to talk about today, this is CSE 519. I'd like to start off by talking about the, the homework 2, okay, which is went out last class. It's an assignment about to be done individually about, basically getting you used to exploratory data analysis in Python. The one probably not great, but one consequence of how the class schedule works, because I like not to give assignments during the second half of the semester while you're working on your course project. I can't give assignments to test every kind of thing that we're going to be talking about. Instead, what I kind of try to do is I kind of front load certain assignments, certain things we haven't necessarily talked about too much. So you get experience, and maybe you'll later see where you might have done wrong when we do more of it. But so the first assignment is designed to go and give you a basic overview of a data science-like project, even with stuff we haven't completely talked about. So what is the assignment? It's based on the predict future sales task on Kaggle, where you're given data from a store and you want to try to predict how much will be sold for every product and store. I gather it's a network of stores. And what are the basic tasks? Again, you guys have to set up your own Python environment. Details are here. There were some clues last time in the in the student presentation. What are the tasks I want you to do? First thing I want you to do is to look at the data that you're given, okay, and try to get a feel for it. Try to make sure you really know what's there, and make sure that you look for possible anomalies or things in that data that aren't right. If it's a store that sold minus 17 items 1 week, what does that mean? Is that something, I mean, I don't know if that data is in there. Can stores sell minus 17 items in a week? Who here says yes? Who here says no? Okay. And the answer is with returns, yes, you can sell minus 17 items in a week. Okay. But is that something that your model wants to know about? Or, if you're trying to predict sales, for example, is sales supposed to be independent of returns or not? There may be things there that you have to clean up. I have no idea that if they have returns in that data or not, but that's the kind of thing I want you to try to think about. And we will talk about cleaning fairly soon in a couple lectures. But you have to, I want you to analyze things by time. Now, it says that the date field, it warns you that the date field is in a funny way. That's part of cleaning, okay? Why is it that they have the form day, month, year? Okay, in America, we're used to month, day, year. Which way makes more sense? Probably day, month, year. Okay, I'd always make, but that's not the way we do it here, not what we're used to. And if you interpret the dates wrong, you get something kind of funny. Okay, item number 3, it was supposed to be talking about analyzing. I want you to try to take a look at these things and try to look at the items and see what kind of things are selling the most, okay, what by month, and see if you learn anything about that. One thing to notice is that the the names of the products are listed in Russian in that data set. So how are you going to go and analyze the items into, so that I can understand it? I need it translated into English. What is the best way to get the Russian translated into English? One way is to learn Russian, okay? And so what might be one thing that you guys can focus on over the next couple of weeks? Or is there some other approach that might be possible? Any ideas? Okay.
Google Translate API.
Okay, it's possible that there is an API for that, okay? And that's the kind of thing that one might want to try to look out for. Okay, what do I want to know? I want you to look at how prices change over time, okay? And what happens when prices sell, prices get cut, okay, or go up. Do people buy more, buy less? Now, you may have taken some economics and may have an idea as to how that works, but I want to see it in the data. And again, I want to see basically data about playing around with the data, trying to manipulate it to find out certain things. What's the number of days since it was released? Okay, is an item that's been in the shop for a long time. Does it sell more or less than an item that's been in the shop very recently? I want you to, for number 6, create a data set, a visualization that shows us something interesting about this data. I claim there is going to be something very interesting in that data. And there are going to be many things that if you start to play with it and learn with it, you will see something. I want you to make plots, a plot that tells us something very interesting about the data set. And I will warn you that I usually go and when I start teaching visualization, I start by showing you the 5 best plots produced by the class and the 5 worst plots produced by the class. So if you don't want your plot to be under the worst plot, I want you to try to use some thought. What is it that's going to be interesting from the data set? Try to find something interesting. For item 7, I want you to start to try to build a predictive model. This task was to predict how much of the items are going to be sold, okay? I want you to try to build some kind of a predictive model, okay? And I give you some ideas. Linear regression is probably the easiest way to do it, okay? It's calling an API. Again, it won't kill you to look in my book a little bit ahead in my book to learn about what linear regression is or something. But I want you to try to build some kind of a prediction model, okay? And, I write you basically, for this part, I want you to play with the model, explain to us how it works, and what the accuracy is, okay? And there is a technique when you're doing modeling that's very important, called KISS. Does anybody know what KISS stands for? Has anyone ever heard the acronym KISS?
Keep it simple, silly.
Keep
Or
it
stupid.
simple. Usually the last word is
Yeah,
stupid. Stupid, okay? But what is the point? The point is not that you guys are stupid, but it is an idea that it's supposed to be that modeling, I start out by doing simple things, and then I add complexity and see whether it makes a difference, see why it should make a difference, okay? That said, we're going to talk a lot more about modeling over the course of the semester, but I don't want people to start out by thinking, oh my God, I got to do, got to build a deep neural net, I've got to do all kinds of things here, okay? Start simple, okay? And then see if there are ideas you have to add complexity to make it a little bit better, okay? Any questions? We'll talk about that. What is the 8? 8 says, finally, you can submit this thing to Kaggle, okay? And I want you to take your final model and submit it. And I want to know the scores on your, your final submission. Now, I don't want people to cheat and obsess about their submission. Again, there's ways to cheat on this competition by going, if you want me to start writing, you could probably find other groups that are submitting. There's undoubtedly code available on the net for doing this kind of thing. Again, I want you to try to do this honestly. It's important that it be done honestly. And I want some groups of people are going to be more experienced about this, okay? But I want people to try to build a good model that they trust, that they like. I don't want them to go panicky about, oh, I've got to get the best Kaggle score. but I do want people to try to build something that they like, and that they learn something from. Any questions? Some question about, do you have to use your CS account for a Kaggle? I don't see any good reason not to use your CS account for Kaggle. If there is a good reason, let us know. Okay. When it says step 1, what data are you merging together? Where do I have the word merge? Okay. Merge the data into one data frame. It may or may not be organized as one data frame. Okay, but that is kind of a suggestion that you should be starting to use pandas and you should start play with it. I do not know. Take a look at exactly what data is there and see what you can figure out. Okay, it may be that there is only one data frame, in which case that might be easy, but it may be that there's other ways of representing it. Any questions?
Just just wanted to confirm that for the anomalies, as we discussed for the negative numbers, that there could be returns, but we will assume that we are not considering the returns and remove the negative
No,
numbers.
first of all, what I want you to do is I want you to do it the way you think it should be done.
Okay.
Okay. So one thing that is true about this course, and that students hate about it, is that this is somewhat open-ended. Okay, your goal is to build a model for doing this. There's many ways you can do this. Okay, and one of the things that's true with data science is that there isn't a quote unquote right answer. There tend to be a lot of wrong answers. Okay, so things that are probably bad practices to try to do, and that we're going to hopefully learn how to avoid. But there's multiple ways to do this that could be sensibly. I just came off the top of my head with this thing about returns. I have no idea if there are returns. I don't know if it's a bad thing and for that there be returns. Okay? But what I will say is that when you're looking at data, there often are, and we'll talk about cleaning in, maybe it's a class or two. Okay? That there are things in there that you have to be aware of. Maybe that need to be fixed. Are there nulls in the data set? What does a null mean? Okay, this may be something about cleaning. Okay, are there other things that are going on? Okay, any questions about that? And one thing I do want us to do, I'm very happy at the beginning of class every day, is if we have a discussion about what things people have found that seemed interesting or weird to them in the course of this data set. I would like to see there be a discussion about this. And I don't want people to get too proprietary about, oh my God, I don't want to let any of my classmates know anything because they'll give them an advantage or anything like that. Okay? I think that if you have a particular issue, I think it's interesting. If you see something, I think it's interesting for us to discuss it in here. Any questions?
What's a reasonable complexity for a model you expect us to build?
What is a reasonable model?
Yeah,
Well,
I'm guessing just simple linear regression doesn't work, right? So
what I'm going to guess is that an intelligent linear regression probably will work just fine. Okay, I mean, none of you should win the competition. Okay, let's start this. Make this clear. I don't expect anybody to win the comp. I don't even expect anybody to do that well. Okay, unless they cheat. Okay, what I do want is to have people think a little bit about it. Linear regression is a perfectly powerful technique if you're using it in a sensible way. Okay, and I want you to think a little bit about it. What have you done to the variables? What have what variables seem like they should be important? Okay, does the model that you're making look like it's making sense on some level? Okay, I think that one thing that I think that is true is a lot of the, a lot of what is, going to be involved here. I'm less worried about your machine learning magic than I am worried about you trying to understand what the data set says and trying to build a model that you kind of understand and do. Okay? Any questions about that? This we will figure out with time. Okay? Any other questions about the homework? Okay. Okay, so I want you guys to think about it, and hopefully that will, it will be, there will be something good there. Okay, let me now end share. Boom. Let me now see if I have the power that I thought I had to go to my second technology. Boom. Boom. No. Okay, hold on. Now, oh wait, now I'm in big trouble. Okay, now it looks like I am in trouble. And let me see if that's gonna work. Okay, maybe it worked now. Ah, bingo. Great. Okay, do you guys see my screen?
Yes.
Okay, good. Okay. Any other questions about anything data science-y, or let me now try to move this around. Okay, and I think there's a way I should be able to see participants. No. Hold on one second. Bang. Okay, good. Okay, so what I'd like to now talk about is, actually, hold on. Hopefully this is right. Okay, good. Let me just try one other thing here. Yeah. Okay, so what I'd like to start to talk about is correlation analysis. And correlations are the, one of the, primary ideas, ideas that kind of drive all of predictive modeling. We say that two factors are correlated when values of X have some predictive power on the values of Y, okay? And, the correlation coefficient of X and Y is a measure to the degree to which you can predict Y as a function of X or X as a function of Y. Correlations, or this predictive power, is kind of symmetric when it comes to correlations. And this correlation statistic ranges from a -1, meaning two things are inversely correlated, to 1, meaning they're completely correlated, where 0 is the score of something being uncorrelated. So let's just take a look at what is the Pearson correlation coefficient. This is a measure of correlation that is probably the most common one used. It says that the correlation of actually, let me see, the correlation of two arrays of numbers, or sets of numbers, X and Y, are the sum, if we have n elements, each of which is has an x value, x of I, and a y value, y of I. The correlation is going to be the sum over all points of xi minus the mean of the x values, okay, times yi minus the mean of the y values. Now, what's interesting, this quantity on top is called the covariance, okay? And we will see it a couple of times in this course. But what's interesting about this, okay? What that statistic is measuring is something about how in sync, okay, the values X and Y are. Basically, if X sub I is greater than the mean, and Y sub I is greater than its mean, okay, then you get a positive number times a positive number, and it makes a positive example contribution to the covariance. if x sub I is less than the mean and y sub I is less than a mean, both of these terms are negative. Negative times negative is positive. Two negative, if both of them being less than their means, makes a positive contribution to this covariance. Now, if one of them is above the mean and one of them is below the mean, then you get a positive number times a negative number, and that makes a negative contribution. Does everybody kind of see this? So that, so that if the two variables are in sync, when one of them is big, the other one should be big, and when one of them is small, the other one should be small. Okay, this kind of measures the idea of a positive correlation. If, on the other hand, they're in random orders, these, if you think about it, if it was random, half the time it would be positive and half the time it would be negative. Okay, they kind of offset each other when you sum them up, and that's why you would get a 0. Okay, kind of sort of that if they're uncorrelated, we would expect this thing to go, the numerator to go to 0. The rest of the correlation coefficient is kind of dealing with the variance of the values. Okay, remember we talked about the variance. That was something like the key term there was the sum of the sum of the difference, the sum of squares of the difference between the element and the mean. And the square root of that was the standard deviation. So it's sort of like we get the this covariance divided by the standard deviation of the main, the x variables divided by the standard deviation of the y variables. And these standard deviations are what serves to normalize the covariance. So it has the magic properties that it can't get any bigger than 1 and it can't get any smaller than -1. Any questions about that? Any questions about what the Pearson correlation coefficient is? Why do we call it the Pearson correlation coefficient? Question, first, was there a question?
I just wanted to know what does the magnitude of the covariance actually represent? I get that the sign represents the positive or negative correlation, I guess, but does the magnitude of the covariance denote anything?
The magnitude of the covariance doesn't actually, change anything. So it's not bounded, okay? It has to do with, let us think about it. Is your covariance, one way to think about it is, suppose I wanted to measure the correlation between height, the covariance, let's say between height and weight, where for people in this class, where I measure your height in miles and your weight in tons. Okay, all of the mean the mean of people's weight height in miles is very small, right? Xi minus, your number, it's going to be very, very small. Does everybody agree that the difference between your weight in the covariance, if I measured your height in miles and your weight in tons, would be very small, whereas if I measured your height in microns, which are, I guess, a millionth of an inch or something like that, and I measured your weight in grams, that would be a very big number. Does everybody see that the covariance itself, the scale, doesn't really mean anything easily interpretable unless you normalize it by the variance or the standard deviation, which is really what we're dealing with here. Okay, so that's why we have this correlation coefficient. That's why we do the normalization. So it's convenient to talk about it from plus 1 to minus 1. Any questions?
Is it a good way to think about it just like the cosine similarity between the two variables after you shift their mean to 0?
So one thing that is true, which we will actually talk about this, when we talk about geometric interpretations of things later in the semester. Cosines also vary between -1 and 1. Okay, if you remember your trigonometry, and in fact, there is a way to interpret this as being, that if you have as kind of the cosine of the vector of, but between the two vectors, okay, of the x variables and the y variables. So there is a way to interpret it like that. If you like it, that's good to think about. Any other questions? So what are correlations mean? That's, I think, something that I want people to internalize. So what is the, you probably have in your head some ideas of variables and how well they correlate, okay? Actually, maybe, for the height and weight, would someone have to take a guess? What was the correlation coefficient between the height and weight? Okay. Does anybody have a number? It's a perfectly reasonable question. Do we think that when people get taller, they usually weigh more? So that would mean it's a positive correlation, right? And how big a coefficient do you think that is? Someone have a guess? It's important to develop an intuition for this, and so that there's a difference between what is a strong correlation and what is a weak correlation. Okay, so one thing that there's in the United States, the test you take to get into college is the SAT. And they try to, pick students that have high SAT scores because they say it predicts your grades the first year in college. In fact, according to what I saw, the correlation between freshman grade point average and SAT was 0.47. That's a pretty strong correlation. Okay, I think that it's pretty clear. Do I believe that that's a real effect? I believe that's kind of a real effect. Does this mean that all students that did well on their SATs are going to have good GPAs when they get to college? Some of them are going to discover drinking. Some of them are going to discover all kinds of things. Okay, and their grades might be bad. And some people may have had a lousy day when they took the SAT. And their SAT scores don't really reflect their ability. And some people work really hard, and so this is kind of, shows to me that's a serious correlation, okay? But it's not a perfect correlation. Another correlation I liked was that the SAT scores and how much money the parents make. Okay, the correlation here that I read was 0.42. What does that mean? That means that I would do almost as well at predicting your GPA if I threw away your test score and asked for your father's tax return. Okay, that's kind of an interesting thing. There is predictive power, for better and or probably worse. Okay, in knowing about economic status, that's roughly as strong an effect as the SAT scores. In fact, it's probably true that the SAT scores correlate well with your parents' economic status. It doesn't have to be the case, but if I were betting money, I would say that the people who got good SAT scores quite likely were able to afford certain test preparation. There's historically a correlation there. Any questions about it? Okay. What would be the correlation between how much income people have and their incidence of coronary disease, heart disease? Okay. The correlation here was minus 0.71. What does it mean when you have a negative correlation? What does that mean? If it's a negative, if it was a positive correlation, as income went up, coronary disease would go up. A negative correlation means that when income goes up, coronary disease goes down. Okay? Can anyone think of reasons why that might be a negative correlation?
Better medical care.
Better medical care, right? That, that if you're wealthy and you're having a heart attack, you don't hesitate to go to the doctor for money. Okay? Any other reason? Better food, okay? That healthier food is more expensive than the cheapest food you can get, okay? And that would be something, okay? Access to exercise is often, who can afford a gym or something like this. So that is a very strong effect, okay? And that's something we see. Smoking and death rates. This was between countries. The countries that have the more smoking have a lower lifespan, okay, or higher mortality rate. That was an equally strong effect, but that was a positive correlation. Now, does violent video games cause violent behavior? You can imagine that this is the kind of studies that, I'll say your parents worried about, okay, where you spend your time playing video games, killing people on video games. Is this going to make you a more violent person? This is one thing that is something people were concerned about in studies. The correlation of the study that I showed that it was a 0.19 correlation. What did that mean? That yes, if you watched more video games than somebody else, you were probably more likely to have violent behavior. But the effect was very low. Okay, the correlation is weak. Okay, I shouldn't send you to prison just because you watch a lot of video games. Does everybody kind of get that idea? Okay. So it's important to get some kind of an intuition here. And whether this, by the way, is probably not, this number 0.19 is probably not the final word on this matter. That was one study by one person, okay? The fact that this is an area that people still debate tells me that other people get different results. I'm not necessarily telling you to give up video games, okay? But does everybody kind of get an idea of what the interpretation of these correlations are? Any questions? It's important to have an intuition, I think, about what these things mean.
When do we call a correlation value to be significant or strong or weak?
Okay, so the next couple of slides are about strong and weak. You use two different words, and that's kind of that is why I'm going to have two different slides. There was this notion of a strong correlation versus a weak correlation. And there was a question about kind of when was it significant? When does it mean something? And there's two different notions that kind of are distinct ideas that we have to keep straight in here. One is a question of predictive power in the sample that you're given. And the other is a conviction of how much do you believe this correlation reflects reality. Those are two different kinds of things, okay? Suppose, let's say I wanted to establish a correlation between IQ and height, okay? Let's say I took a look at this here. And I'm gonna ask you, okay, actually IQ, I want you to make up a number, so don't tell me anything. Idan, make up a number for your height and make up a number for your IQ. Or
I would say 5'7" and 115.
115. Okay, very good. Okay, now I want somebody who's shorter or taller. Somebody who's got a different height. Who will volunteer for a different height? I see Michael is the one who I'm staring at here. Michael, how tall are you?
6'2".
6'2". And how smart do you want to claim to be?
80.
80, okay. So what have we seen here? We have 2 points here, okay? What you call, the guy who's 5'7" has an IQ of 115, and the guy who's 6'2" has a IQ of 80. Does height have a positive or negative correlation with IQ? By
Negative.
that statistic. Negative, okay? And what is the correlation coefficient you're going to get when you plug it in that formula? It is at a correlation of 1. It's a perfect correlation. Have we now learned that IQ is perfectly negatively correlated with height, and that basketball players all have a IQ of 6, okay, because they are giantly tall? What is the problem? There's 2 different issues. One, there's a question of what is the predictive power of a correlation? And there's the other of how much do we believe that correlation? And that's a significance issue. So let's go through what I want to say. And I think that in this case, that particular example, it's the significance issue that is wrong. But let's take a look at this. In interpreting what the power of a correlation is, okay, we usually interpret it by something called an R-squared value. R is the correlation, okay? R-squared estimates the fraction of the variance in the second variable that is explained by the first variable in a simple linear regression. Okay, that's one way to think about it. So if you have a correlation of 1, what is the R-squared? 1 squared is 1. It explains basically all the variance, right? If you have a perfect correlation, if I knew how tall you were, I knew how smart you were, okay? If there was a perfect correlation, right? Let's say the correlation was 0.5. What would the R-squared be? What fraction of the variance is explained by height versus IQ would be explained if we had a correlation of 0.5?
0.25.
1/4, right? Does everybody see that this is a nonlinear thing? Remember back to that video game, okay, explanation when I was telling you that it was a 0.19 chance of correlation between violence and video game stuff? Suppose that's true. How much of your tendency to violence is explained by that correlation of 0.2? What happens when you square 0.2? What do you get?
Yeah, 4%.
0.04, 4%. That correlation of 0.2, which looks pretty impressive, okay, even if it's right, only explains 4% of the tendency towards violence, right? There's other reasons that it would presumably explain more of the tendency towards violence, right? Okay. So one thing to note is that correlations, although they are positive and interesting, okay, when you square them, you realize that it explains less of the variance. You know, a modest correlation explains less of the variance than you might think it does. And that's a lesson to internalize here, okay? Now I ask you, what was the correlation between height and weight? When I looked it up, it was approximately 0.8. So that's a pretty strong correlation between height and weight, which I guess you guys would imagine. Obviously, there are short, heavy people, and there are tall, skinny people. But in generally, there is a strong correlation between height and weight. But a correlation of 0.8 means that height explains about 2/3 of the variance in weight, okay? Which is less, still substantially less than 80%, which you might think when you had that correlation. Any questions about that?
Why not just take the absolute value of correlation?
Why don't we take the absolute value of the correlation? So the absolute value of the correlation tells me something about the power of the connectedness. but it doesn't tell me about the directedness. Okay? If I told you that there was a correlation, the absolute value of the correlation between height and IQ was 1, you would say, great, I can find out how smart somebody is by, by measuring their height. But you don't know whether the tall people are smarter or dumber, right? So the sign is conveying a lot of extra information. Now, the magnitude of the effect for predictive purposes is in fact the absolute value, but the sign matters because it tells you the direction of things. Any questions about that? So
Why does it matter to know the amount of variance that it explains versus just the strength of the correlation? Like, when you're interpreting it as a human.
Well, when you're interpreting it as a human, arguably you're saying I'm capable of taking a square of a number by myself, okay? And that will help me measure it. But people are not as good at dealing with nonlinear things. I am surprised a 0.19 correlation, if I get that in a paper, I'm very proud of it. I say, look at this, I got a correlation, okay? But on the other hand, noting that it explains only 4% of the variance is kind of a, puts it in its place a lot more about how useful it is to make predictions. It tells me that if you've got weak correlations, you're not going to be able to make very good predictions, okay? Now, what do I mean about variance reduction? That's what this kind of is. And I guess I want to make clear kind of what that actually means. On the left here, do you guys see my cursor when I'm moving around? Yes, you see me move around. Okay, that's good. What's actually happening here? We have what looks like a great fit between X and Y, okay? That was a correlation of 0.94. Now that's really a strong correlation. Everything fits nicely on a line, right? Now, if you want to think about what in terms of variance reduction, the variance of these values on the left is pretty high. Why? Y ranges from minus 0.4 to 0.6. Okay, the variance in the y-axis is pretty reasonably large. Now, this line is the best fitting line that passes through those points. Remember, we're going to talk about linear regression, linear fits. The correlation is kind of governs how good of a linear fit there is to the data. When we have the best fitting line through the data, we can talk about the residual, the difference between the y value and the prediction. Okay, if we think about it, that line is a value, will have a value y as a function of x. If we want to predict what the value of y should be for this point, if we know the x, if we have a line, we can make a prediction. The error in the prediction is y minus the value that our line gives us. On the right is the plot of the residuals. Notice that the differences between our prediction and the actual values, the range of that is a lot lower than it was on the original points. The variance of the y values on the right side of this, okay, is much less than the variance on the left side. So when we say basically that 1 minus r squared is equal to the variance of the residuals divided by the variance of the original values, okay? And in this case, the variance here, okay, this particular value of the correlation of 0.94 would explain 88% of the variance, okay? And that kind of makes sense when you see that again, what the range of the values are on this side is about up to 1. The range on this side is a lot closer to 0.2, and things are much more centrally located. Any questions about what it means to explain the variance? In some sense, again, one way to interpret it, we care about correlation for how good a prediction we can make, right? And this says how good is the linear model. The variance of the residuals says how much stuff is there still to be predicted, okay, that we weren't able to predict with our simple linear model. Any questions? So when you think about how strong a correlation is, you really should be thinking in terms of R squared for a sense of its predicted power. Any questions? Okay, boom. The other question that comes up that is sort of orthogonal to predictive power, and maybe, you know, it has to do with this idea of statistical significance. We will talk more about statistical significance in a small number of weeks, okay? But basically, it wants us to know, it's a measure of how much do we really believe the observed correlation in our data set. I am going to guess that none of you believe, I'm going to go out on a limb and guess none of you believe that my perfect correlation, perfectly inverse correlation between height and IQ really holds. Why are you suspicious of that? Well, one is I think you realized one of them was lying when they said their IQ was 80, okay? But I think the bigger reason was because you knew that there were only 2 points that were taken, right? A law of statistics, if you want a perfect linear fit between things, measure it at only 2 points, okay? Where a observation becomes interesting is when the correlation is high enough that it is very, very unlikely we got a correlation of that magnitude by chance. That's kind of what the issue that significance is talking about, okay? And so when you talk about significance levels, people will talk about a significance levels of 0.05. That is saying that the chances of me seeing this strong a correlation by chance, okay, is less than 20%, 1/20th, 1 over 20, less than 5%. Okay, that's what it means to be significant at a 0.05 level. Okay, so what does this figure show? This figure, okay, is going to kind of show that as n, the sample size, gets larger and larger, a correlation, an observed correlation, can be smaller and smaller for us till we start to believe it. Suppose there was a perfect inverse correlation between height and IQ. Okay, you weren't impressed if I showed you 10 people, 2 people, and they showed perfectly on the same line. On the other hand, if I took 10 of you, and now, son of a gun, if I took your heights and your IQs, they fell inversely on a line perfectly. If you have a very strong effect, a strong correlation, it starts to look interesting with a smaller number of people till you start to believe it isn't by chance. For a very, very weak correlation, you need a large number of people till you kind of believe it is not by chance. How many thugs do I need, okay, to try to figure out, if I ask them how much crime did you commit and how much video games did you watch, okay? To see that kind of a correlation, that's a subtle thing. I'm going to need a lot more evidence before I believe that there is really a relationship there than if there was a very strong correlation. And so the significance is a function of how much we believe. How strongly do we believe that that correlation is not a result of random sampling, okay? That in fact there is that it is not, that there is a real correlation there, okay? Not just a sampling artifact. Any questions about that, what significance is? Okay, so this is kind of what's interesting about this is you can prove significance, that there is some kind of a non-trivial relationship between things. even if you have a large enough number of samples, if there's a non-trivial relationship, you might very well be able to prove there's something there. That's a significance. On the other hand, what's the predictive power of a correlation? If you have a weak correlation, the predictive power grows, according to the square of that correlation, right? Which means that it will be a weak correlation squared is a very, very weak effect, okay? The significance is there something there, okay? The correlation measures how strong is that there, if you really believe it based on your sample data. Any questions about what the difference is? So when we talk about like big data and machine learning and complicated machine learning models, a lot of what you're looking for, you're hoping that in a big data world, you have lots of different features, each of which will have a weak effect on making your predictions, okay? But the hope is that in aggregate, if you have a lot of weak classifiers, so long as they are independent of each other, okay, then they can add up to having a significant predictive power, okay? But you need a lot of weak class features, and they need to be independent. If they're making the same mistakes, which would be the case when they're dependent, then having more of them doesn't do any good, right? If I knew your height in meters and I wanted to try to predict your IQ, if I also give you your height in inches, is that going to help? Suppose I give you a feature set that has your height in meters and your height in inches. Would that give you more power than just a height in meters?
No.
No. Why not?
It's the same metric.
Same metric, I would say, because they are perfectly correlated and they are not independent of each other, right? So that's where this stuff comes in. Any questions about significance or about significance or R squared? Do you see that they're measuring different things? And do you see that both of these things are important?
Professor,
Yes.
for the previous slide, what if we care more about sub-region much more than others? Would it still be a good method?
Okay, so what you may be saying is, suppose, let's say I want to try to predict the intelligence of basketball players, okay? And basketball players operate a small part of the height space, right? They are all 6'5" or above, okay? Maybe you're saying that maybe there's a strong correlation between IQ and height in that range that doesn't hold over the whole thing. So what that's really getting to is that there's sometimes not a linear relationship over the whole range of variables, okay? And that is why there is another form of correlation that is measured that is important to know about, called the Spearman rank correlation, okay? Not everything is, sometimes there is a positive relationship between two variables that isn't necessarily linear, okay? And the Spearman rank correlation kind of counts it by, it counts not how well does a line fit the data, but it measures how many disordered pairs are there. So suppose, let's say that between height and weight, there was a negative, we expect a negative, well, let's say we expect a positive, let's say between two variables, we expect a positive correlation. If it was a positive correlation, then what do I know? If I had the value 5, 100, and I have the value 7, if there was a positive correlation, okay, what would we expect that we know about the missing value here?
It's bigger than 100.
What?
It's bigger than 100.
It should be bigger than 100. If I told you that it was 95, that would these two would be a pair that is out of order, right? And the Spearman rank is counting the number of out of order pairs instead of just how well it fits a line. Okay? And here are three data sets that to me are kind of interesting. The center one has a Spearman correlation and a Pearson correlation, both of which are 0.94. Okay, those are very, very high. This is where there is a strong relationship between the data, okay, the X and Y, and that relationship is measured by them being fit on a line, right? What about the situation to the right, to the left, okay? This angle bracket. Does everybody see that as X gets bigger, Y gets bigger, right? Does it do so in a linear manner? Maybe to a point, but then suddenly it goes into outer space, right? That after you get to 5, suddenly Y changes quite dramatically with this. In this case, there is no good line that passes through this data. And yet X, properly interpreted, completely predicts Y. Does everybody kind of see that? So the Spearman correlation is 1. The Pearson correlation is, positive, but 0.7. Okay, any questions? Look at this example to the right. We have a lot of points that are on the line, but one outlier. Does everybody kind of see that? Does this, how far that outlier be affect the correlation? Well, in a Pearson correlation, where you're measuring the difference between a point and you're measuring the magnitude, the difference between the value and the mean, and you're squaring it. One outlier point really lowers the Pearson correlation. Does everybody kind of see? Think what's going to happen if I take this point and I lift it up. Okay? It's going to pull that regression line up to try to satisfy that point. Okay? But, that's going to then make the other points unhappy. So it's going to be reluctant to try to do that. But does everybody see that having one outlier has a big effect on the Pearson correlation? Here, because the outlier is it's a biggest value and it's to the right, there's only one unhappy pair caused by that outlier. This one is bigger than this one. That's the only unhappiness that is being caused by that point. And it doesn't matter how far I can send this thing to the moon, and the Pearson-Spearman correlation wouldn't change. Does everybody kind of see that? So the Spearman correlation is a good way to measure effects that aren't necessarily linear. Okay, any questions? And again, some of you are going to build models that are not necessarily linear. So Pearson correlation is a good thing. In fact, the Pearson correlation can be computed as follows. Okay, if we let the rank of a variable be its position in sorted order, okay, we say that the distance of I, the displacement, is the difference between the ith value in the X and the rank of the ith value among the X values and the rank of the Y value among the Y values. If something is ranked very highly among the X values, we would expect it to be ranked fairly highly valued on the Y values, and the difference here would be small. Okay? So basically, this is measuring the sum of the differences, okay? The sum of squares of these deviations and we divide it by 6 over, by n times n squared minus 1 over 6. This is the thing to sort of normalize the number of pairs, right? What is the worst that this could be? Well, if everything could deviate by a rank of at most n, right? The x value could be the biggest and the y value could be the smallest. N squared is going to be n squared. The sum of n of those terms could be order n cubed. This normalization thing is a function that is order n cubed. It's to normalize that so it ranks between -1 and 1. And another way to interpret the Spearman ranks is it's the Pearson correlation between these rank values. Okay? And if that's enough for you, if you believe that, that's enough that should convince you that it lies between -1 and 1, because the Pearson one does. Any questions about the Spearman correlation? Okay, so quite often, when I look at a variable that I think has a good dependence, I will sometimes look.
Question,
Yes.
quick question. What's the 6 means in the equation?
What is the 6? The 6 is the magical constant such that the sum of the worst case, remember, I need the sum of the most disorder to add up to be, I don't remember if it is, I guess, okay. If there's the most disorder, I want this to be -1, right? If they're completely inversely done, I want my row to be -1. That means I want this thing on the right to add up to be 2 when it's maximally bad. And so what I claim is that the 6 comes from 2 times n over n squared minus 1 over 3, which is the normalization for the worst you can get for the sum of squared distances there. Any questions? Any questions about the Spearman correlation? Okay, I claim it's a useful thing to deal with. Okay, one thing that is maybe the most important thing to know about correlation and causation is that correlation does not mean causation. Okay, a correlation is an observed relationship between the two quantities. When there is a relationship between the two quantities, it could be that X causes Y. It could be that Y causes X. And it could be that X and Y are both caused by something else, right? Remember back to our SAT thing. I think we saw that SATs correlated with grades. Money correlated with SATs, okay? Is it that money caused, so exactly what the causations are, sometimes there is a third factor, okay, that is causing both of the other two, okay? And we don't really know about causation, okay, just because we have a correlation, and there's all kinds of cute examples of it, okay? In general, in a well-run police department, the number of police you have in a district correlates positively and strongly with the crime rate in that district, right? Now, is it that the police are causing the crime, or are the police reacting to the crime? Okay, I'd like to think that the reason you have, again, this is complicated, the world's a complicated place. I'd like to think that the reason you have more police in a district generally is that that's where the crime rate is. It's not the police causing the crime. It's the crime causing the police. Okay? Not perfectly, but these things. And there's a bunch of great cartoons kind of illustrating this point. So I encourage you to read through those and when you review the notes. Okay? Any questions about that? We use correlation to make predictions. We don't necessarily know that the predictions are there or not. Any questions? Actually, I suddenly see that Okay. Actually, it's fine. I suddenly see that there were a lot of comments that for some reason I wasn't getting on the chat. Any questions that we need to deal with? Okay. Now the question is, there's a question here, is data science trying to find causation? Well, it depends upon who you talk to. Okay. To a certain extent, you're trying to make predictions that are going to be accurate predictions. And it's not clear that you necessarily care whether you know the root cause. So some people who are doing machine learning will be very happy to make correct predictions without having any reason to, care about what the actual causations are. Okay. On the other hand, it's often useful when you're building a model to, to understand the world. You want to know what's really causing it. So maybe you can manipulate the right thing. Okay. If sales are dropping, okay, and it correlates with 96 things, I want to know what the right thing, maybe I could predict my sales accurately, but I'd like to know what is it that's really causing the effect. So in general, it's good to know it. There's a question of when would correlation mean causation? As far as I'm concerned, I don't, I am suspicious of causation without an underlying understanding or belief as to why this is, okay? So there are statistical methods that purport to try to measure causation. There's this notion of Granger causality, which is kind of a statistical method, but I don't really trust these very much. I guess I generally, when do I think about causation? I look for correlations. I try to think to myself, does it make sense that this manipulates this? Sometimes you test, social scientists will often test causation by then actually changing it. If I think that more police in a district causes more crime, what would be the intervention that I should do if I want to test that theory? Maybe I go to a district, I bring in more police and see if the crime increases. Or I cut the number of police and see if it goes down, right? That's where I start to establish causations. If I see that I can manipulate one and change the other, okay? But that's a different question than what have I observed, okay? So this may not be satisfying, but I don't think that in general, I can tell too much from, I don't trust causations. I trust correlations, and I try to find interpretations that convince me whether it's right or not. Any questions? I will notice when we talk about police, again, there's questions about what causes crime. In New York, there was a time in the 70s when New York had a terrible crime rate. In the 80s, terrible crime rate. The crime rate went down dramatically and amazingly from the 90s till today. And if you talk to social scientists who study it, they generally will say they have no idea why. There's all kinds of different theories as to why. The people there are a lot of people who say we hired more cops, that's why. Someone else will say, well, wait, but drug use went down. People stopped using crack, okay? Some people will say, well, there were fewer young people, okay, born then, and it's young people who cause crime, okay? So there are a lot of correlations that might be there. Trying to determine whether it's really causation is actually surprisingly, frustratingly hard. Any questions? Okay. One last thing about correlation that I want to show you that's kind of an important tool has to do with periodicity. Let's say, hypothetically, you were working with data on sales for maybe a homework problem in a data science class, okay? And if you had, I don't know what the range of time period covered by that data on the Kaggle challenge, but does everybody, if you studied sales data in the United States for many goods, you will find a surprising peak around every December. Why is it that sales go up in December? Does anybody have any ideas?
Holidays, Christmas.
Holidays, Christmas, people buy things for Christmas. How would you know if you looked at a sales figure, boom, boom, boom? How would you have a sense that, what cycles there are in data? In sales cycles, is there a cycle that goes with the week? When you sell things, do you think that there are more things sold, is the same amount of goods sold every day of the week, or there's a within week effect?
Probably depends on the goods you're selling.
Depends upon the goods, but a lot of things people buy what things are very much dependent upon the day of the week? Can anybody think of a good that is probably very dependent on the day of the week, at least in normal times?
Alcohol.
Alcohol. My guess is people buy more alcohol on weekends, okay? So yes, so I would expect that alcohol would blip every week, okay? What is something that probably sells less, not correlated with the weekend so much? Are there any goods that people can think of?
Business-related goods.
What?
Business-related goods.
I didn't hear that, but what?
The business-related, so like...
Business-related goods probably sell during the week, not on the weekends. There's still a weekly correlation, right? But the number of people wanting to buy Microsoft Office probably drops a lot on the weekends, okay? My guess is there's some things that probably stay the same, okay? Like I'm going to guess that your tendency to buy food probably may very well be relatively consistent during, there's probably still a weekly effect, okay? My guess is your tendency to buy Netflix, to get charged for Netflix, probably you buy it on a particular calendar day of the month every year. Every month you pay your Netflix bill. And if you always pay it on the 15th of the month, it's going to be independent. Netflix probably has very little change in the number of sales each month, if they count monthly sales each week, day of the week. How can we determine these cycles? It's clear that there's going to be weekly cycles, monthly cycles in businesses. A lot of things people buy at the beginning of the month, okay? Maybe because that's when they get paid, or just because when there's renewals. Some things happen every, every 4 times 300. For example, presidential election we have coming up. That happens only once every 4 years. Certain things are going to happen. And the amount of people who go to the local school to vote spikes dramatically over these things. How can we identify these long correlations? These correlations that go with time. We say that a time series is autocorrelated if there is a high correlation between the values at time t and the values at time t plus k. Okay? For a correlation, you need 2 time series. For an autocorrelation, you need 1 time series and 2 offsets. Okay? And the claim would be that if you want to try to identify when there are interesting periodic cycles in data, you think in terms of computing the autocorrelation. Okay? Any questions about that? Do people see what I mean by a shift of a time period? If I take a sales today from the sales 7 days from now, that would let me detect if there is a weekly autocorrelation. Right? Any questions about that? How much computing time as algorithms people does it take to compute a correlation? If you have if you have n items, how much time does it take to compute the correlation of n items? It's order n, because if you look in the inner loop there, you're basically summing up over all elements the difference between an item and its mean. Okay? Now, if you wanted to compute the autocorrelation function, which is the lag, this is the autocorrelation for all possible lags, what is the correlation between the time series and the lag k time series? Okay? This would be how many lags are possible. If you have 2 series of length n, Well, actually, I guess you could say they could look like this. This is where they're perfectly in sync. You could shift this one over n places. You could shift that one over n places. There's something like 2n minus 1 possible different lags between two series. If you wanted to compute it, the autocorrelation for all lags, that would be n times n, or n squared. The interesting thing is that complete set of autocorrelations can be computed in n log n time using FFTs, the fast Fourier transform. This is one reason why people who know about Fourier transforms get excited about them. Because given a time series, you can compute what are the powers of all the lags, okay? And what you would hope to see are that where there is an unexpectedly large autocorrelation, that tells you that the value 7 days ago should be helpful in trying to predict the value now. Any questions? Okay. Any questions about autocorrelation? How you would use correlations to identify what are the time shifts that are meaningful. Okay. And note that when you're building your linear sales model, this might be interesting to know about. If I want to know how many items am I going to sell today, maybe it's a function of how many items did I sell yesterday and how many items did I sell a week ago, right? Now I've got two parameters in my model, okay? And maybe, if there's a strong lag 7 autocorrelation, then that tells me that the week ago might be a better basis for predictions than yesterday. Any questions about that? Any questions about these lags? Okay. Okay, if not, start thinking about the assignment, think about correlations, and we will talk more next class. Okay, thanks a lot.